by Tommaso, who's gonna present to us updates on Shufflecake, an open source tool for creating hidden drives which for plausible deniability. Tommaso is the head of the cryptography team at Horizon Labs.
Okay, thank you very much. You hear me well? Okay, that's great. Very happy to be here. Actually can spoil the part of my introduction, so I will go super short here. That's fine. Okay, so some of you might have already seen one of my talks about Shufflecake. This one is going to be a little bit different because I'm going to focus less on the theoretical cryptographic aspects and more on the design choices and on the updates of last year. Shufflecake is a joint project with Elia, and also we have a growing community of contributors, which I would like to thank here. Okay, so in a nutshell, what is Shufflecake? It's a plausibly deniable disk encryption solution. It's similar in spirit to other tools you might have heard of, like TrueCrypt and VeraCrypt, but with a lot of improvements, both in security and usability. Basically, it aims at striking a balance between the security of ORAM-based solutions that we will quickly see, and the efficiency of and user-friendliness of VeraCrypt. It comes with a cryptographic proof of security, and there are work in progress to add other features. Most importantly, everything is free, as in freedom. So this is completely GPL2 software, and all the community is open. Okay, this is about Shufflecake. How cool is Shufflecake? Well, from what we have seen so far, we got good feedbacks from the community. We presented it at DEF CON. We have a paper at CCS. We ended up on some online discussion venues that you might be familiar with. And as you will see, we have a growing community of contributors that are helping here. Okay, a couple of words about myself. Yes, I'm Tommaso, a cryptographer from Darmstadt. I worked at IBM before and Kudelski. Right now I'm at Horizon Labs. And my focus is on privacy, cryptography, blah, blah, blah. But also I come from a privacy activism background, okay? I use free software. I go to hacker venues and conferences. I use Graphene OS, this kind of things. This is just to say that at any point in time, you can find me in a quantum superposition of more business and less business activities. Okay, and Shufflecake goes completely in the less business area, so nothing of what I'm going to say here is commercial, blah, blah, blah. Okay, so I gave you the short introduction. I'm going to talk quickly about TrueCrypt, VeraCrypt, and then I'm going to jump immediately to the design choices we had to do for Shufflecake and the current and future directions. Okay, what are we talking about? We are talking about disk encryption. As you know, there are plenty of solutions for full disk encryptions. Some of them you might already be using, or with or without knowing that you are, because some of these are pretty standard. But back in the time, they were not so standard, okay? And all these solutions have the common problem that they do not help into situations where your adversary can use coercive methods to extract the password from you. It can be psychological, legal, violent methods. Give me the password or, right? So we want to have some sort of protection here. What kind of protection? Basically, you want to hide sensitive information in such a way that the adversary cannot immediately see that there is information, but at the same time, this hiding has to be plausible. So if the adversary asks you for the password and you say, oh, I forgot it, doesn't work very well, right? So you must have a method to give something to the adversary in such a way that it looks like you gave enough. Typical example is that you have your disk that is encrypted, and you have one password that unlocks decoy data, for example, your cat pictures, and the other password that unlocks the more sensitive data. And for the adversary, there must be no way to distinguish whether you have given password 1 or password 2. This is the basic idea of plausible deniability here. There are some caveats, as we will see, but let's move further. Oh, and note that this is different from steganography. Steganography is hiding the presence of encrypted information. Here, the disk is encrypted. You cannot hide this. So the goal is something different here. The goal is to make sure that you have a way to only reveal something. Okay, how do we do this in practice? One of the first software that implemented this idea in the context of disk encryption was TrueCrypt. This was released in 2004 in an age where full disk encryption solutions were not widespread, okay? This had a troubled history, this software, very shady history, in fact, and it was discontinued in 2014 and replaced by VeraCrypt, that some of you might be more familiar with. If you're not familiar with the story, I encourage you to go on Wikipedia and read the story of this super shady guy, because there's going to be a movie about this guy, I'm pretty sure, because Breaking Bad is a fairy tales in comparison. Okay, so how does VeraCrypt achieve plausible deniability? Well, as I said, TrueCrypt, or I'm going to talk about TrueCrypt here, originally was a disk encryption tool. It means that you know, there is some user data and it's encrypted by one password on disk. However, TrueCrypt introduced another mode, the plausible deniability mode. And this mode works by embedding a second encrypted partition in the empty space left by the first partition. Okay? Oh, I'm giving you troubles if I move. Okay. So why does this work? This works because in all disk encryption solutions, the first step is to overwrite the empty space with random data. In other words, if you don't have the second password, the one that unlocks the secret volume, these two situations look the same to an adversary because you only see random noise instead of zeros in the empty space, right? Okay, TrueCrypt works, kind of, but it comes with a bunch of problems. Some of these problems are reasonable. Some others are more difficult to tackle. For example, TrueCrypt is very targeted for Windows, so it only works with FAT file systems or NTFS with some caveats. And it only offers 2 layers of secrecy. So you have password 1 and password 2. If the adversary sees that you are having TrueCrypt installed on your device, they are not going to be happy if you only give 1 password, so get prepared to a difficult discussion. Most importantly, these 2 partitions that you have cannot be used concurrently, and this creates a problem of stale decoy system. What does it mean? The adversary comes to you, give me the password, you unlock the cut pictures, and the adversary from the metadata sees that the last update of the system was 2 years ago. Doesn't fly very well, right? So, okay. When I point out these problems of TrueCrypt, there are some objections, okay? And as I say, some of them are reasonable, some of them are not reasonable. So let's talk about the non-reasonable one. So first of all, TrueCrypt is dead. I mean, I've been saying before that it was discontinued in 2014. So why are you talking about TrueCrypt? Everyone uses VeraCrypt nowadays. True, but for the sake of this talk, the 2 solutions are the same, because technically they are the same solutions with more transparent governance from VeraCrypt, different key derivation functions, but it's the same stuff, basically. And then there is this other objections like, oh, but using FAT is not a problem. Yes, it's an old file system, but I still use it on my laptop, so why should this raise alarms? Oh, yes, I use VeraCrypt, but I swear to God, I have nothing to hide. I only use it as a full disk encryption solution, so I don't have a second password. Oh, but there are other solutions for Linux, like LUKS. You know that you can also have plausible deniability with LUKS. You just have to do this super complicated and brittle solution that it doesn't really work. No, okay, I'm not interested in discussing these particular problems. These are excuses. TrueCrypt has problems. All right, and that's why we designed Shufflecake. So Shufflecake aims at solving all these problems of TrueCrypt. It's native for Linux, but first of all, it's file system agnostic. So we don't care if you use FAT, X4, whatever. You can use whatever you like. because it works at the block device level. You don't have only 2 passwords, you can have many of them. You can have first password that unlocks the cat picture. No, I don't believe you, give me the real password. Okay, here is my real password, it unlocks my collection of pirate MP3 music. No, I don't believe you, give me the real password. Okay, what will my mom say? This is my collection of adult videos, you know. But there is no way to show that you have a 4th password that unlocks the Panama paper, right? Most importantly, if you unlock all these volumes, you can use all of them concurrently. You can read and write on them at the same time, which is great for usability because now you don't have the problem of stale decoy anymore. For usability, if you have 10 volumes, you don't need to insert 10 passwords. You just need to put 1, and you just put the most secret one, and it will automatically, recursively unlock all the others. And of course, this is free software, so it's released under GPL license version 2 or superior, because we want to be pure. And so yeah, that means that you can also contribute to it. Okay, this ends the pretty much the motivation part. So design choices, operating principle. As I said, this I already told, 1 volume, 1 password, but 1 device can have more than 1 volumes. Cryptography is pretty, there is nothing fancy, okay? Well-established cryptography, AES, Argon, but we can, I mean, we have a cryptographic security proof that this is secure, right? So that's good. How do we implement this in practice? Okay, the design that we opted for is a 2-component solution where we have a kernel module that does most of the job, and then we have a userland application that the user interacts with. Why we split it this way? Well, there are a bunch of reasons. Basically, we can use more updated cryptography in userland, and also it's better for error handling. For example, if you put a bad password, this part should alert the user. You shouldn't log it at the kernel level. That doesn't make any sense. From the operational point of view, what happens is that when the user inserts a password that unlocks data, from the operating system point of view, it's like if you plug a bunch of USB sticks to your computer. And so you just see the new devices popping up. And these devices appear to the user as traditional block devices. So the user can do whatever they want with this. This can be formatted, can be mounted, you can write data. In theory, you can also install more stuff inside, and this is going to be the interesting part later. Let's talk about one security design choices that bothered us a little bit, multi-snapshot security. So what's the problem? The problem is that when you have decoy data and you have the adversary ask you, okay, give me the password to this data, you unlock a certain partition. But this is a problem with solid-state-based devices, because in solid-state devices, you might be aware that when you delete stuff, you are not really deleting that, or at least not immediately. That data is marked as unused and ready to be rewritten over a certain time window. But then this is a problem, because that means that so if you have secret data there, a snapshot of the secret data can survive at different moments in time, all together in the same logical snapshot at the same time. Which means that the adversary, by only unlocking this part, can see from the metadata of the empty space that this space has changed over time, which shouldn't really happen if you don't have hidden data there. And so this gives away the presence of hidden data, and the adversary will not be happy about it. Okay, multi-snapshot attacks. This is a big problem, okay? It's a well-known problem in plausible deniability, and the long story short is that mitigation is very hard. In fact, we also have theoretical results that says that mitigating this stuff is difficult. The only 2 secure systems are ORAMs, oblivious random access machines, or the write-only version of them, which work. I mean, they are bulletproof in a certain sense, but they have extremely low performance. Most importantly, we think that they overpromise on the security. Why? To summarize, the reason why this solution works is that they assume that a read operation do not change the state of the disk. Only write operations do. And we think that with modern SSD controllers, which are extremely complex, whatever, this is a very strong assumption, because do we really have guarantees that there is no some undocumented optimization technique, some cache or whatever, that maybe not even for nefarious purposes, maybe just for optimization, but it's some proprietary technique that change the state when you do read request? This would break your security model. So the only solution would be to use full ORAMs, which are completely unreliable, completely unrealistic. Furthermore, do we really need bulletproof security here? At the end of the day, we only want operational security. We want something that stands in court. Just imagine, you go to court and you know, the public ministry says, okay, our forensic experts prove that you have withheld hidden information with probability 2/3. I mean, your defense lawyer will open up popcorns and start having fun, right? I mean, that's so. Bottom line, like full security, we don't really care. We care about operational security, and the question that we don't have an answer to yet, are these multi-snapshot attacks realistic? Is it something we have to protect against? Okay, we started with this design of Shufflecake, Shufflecake Legacy. Shufflecake Legacy uses AES CTR in counter mode to encrypt blocks of data. Why do we use counter mode? The idea is that we wanted a technique that allows us to re-randomize ciphertext. Why do we want this? Because the idea is that if we can re-randomize ciphertext, we can use some update techniques to make forensic analysis more difficult. It's not going to be bulletproof, because for being bulletproof you need an ORAM, but maybe we can achieve some very good trade-off. However, for doing this, you need to explicitly write IVs on disk. This is cumbersome, takes space, it's brittle. This is not recommended. It's just the first design of Shufflecake. Regardless, we got pretty good performance, right? We got like 30% slowdown over a bare encrypted disk, which is okay for daily use. So the plan eventually for future development of Shufflecake is to go Shufflecake full. What does it mean? Start from the legacy, but add crash consistency by making the writing of these IVs on disk robust, and insert a daemon that over time re-randomizes the ciphertext. Again, it's not going to be bulletproof, but we think it will go in the right direction, so to speak. Open question, should we bother? And most importantly, in order to make it work, we need a formal analysis of the security model, how many snapshots does an adversary have over time, and so on. In the meantime, we have some news. Okay, recently we released Shufflecake Lite. What is Shufflecake Lite? It's the same design of Shufflecake, just instead of AES CTR, we use AES XTS, which is the standard disk encryption mechanism for disk encryption. It's natively crash consistent, it's faster, more space efficient, and right now it offers the same security of legacy, just legacy can be expanded in the future, this one not. But basically what we have is an immediate boost of performance and reliability without sacrificing security, which is great. In fact, right now, Shufflecake works in default mode Lite. Legacy is only supported for backward compatibility. I mentioned good performance. How good? Well, this is comparison of Shufflecake with dmcrypt, which is the standard disk encryption tool for Linux. This is madness, okay? We are almost as fast, and in some cases even faster, than Lux. Okay, this is ready for use today. In fact, we can run it natively on and without any degradation, any performance, bulletproof. So, very good. Let's talk about hidden OS now. everything that I said so far is insecure. Great news. Because even if Shufflecake were 100% secure, what's happening is that your operating system will leak information to the adversary. Why? Because when you open your hidden data, your operating system will do all sorts of nasty things. It's going to start caching stuff, it's going to making logs, and there is just no way to patch the operating system to not do this. It has been attempted before, it's impossible. So the only option is to have a hidden operating system. So to have Shufflecake as the first user interface, and have the operating system booting from inside the Shufflecake volume, which we can because we support arbitrary file systems. So the idea would be to have a system where the user puts a password, and according to which password is inserted, you boot hidden operating system 1 or hidden operating system 2, and in theory, all these systems can see each other and update each other in the background, okay? Now, clearly, this would be the ultimate plausible deniability goal, but you realize how difficult this can be. We have to implement Shufflecake at bootloader time. We have to make sure that the operating systems can update each other. And I mean, it would be really nice to have a system like this. But, you know, this is probably very difficult to achieve. Or at least that's what we thought, but we were wrong. In fact, thanks to the contribution of to some external contributor, now we have not one, but 2 implementations of hidden operating systems. So one is SFLC boot, and one is Reliant. And you can use them now. You can go and try them. And this is great. So SFLC boot, it's basically a Drucket module that is done to modify grub so you can boot your operating system inside a Shufflecake volume. So in practice, what you do is you install your decoy operating system on your laptop. I don't know, you install Debian, and then you create Shufflecake volumes, and then you use SFLC boot to install other operating systems in these volumes. And then at boot, you are asked for a password, and according to the password, one of these operating systems will boot. And it will also see the file system of the other operating systems. So if you want to, move, automatic update is not implemented yet, but can be done, right? So Reliant instead is a much more paranoid solution. It's the extreme paranoia, right? So this one uses cubes. If you're not familiar with cubes, cubes is it's kind of an operating system where you don't have a full operating system. You only have a bare metal hypervisor, and then all your applications are virtual machines. So you can spin up virtual machines as you need them. And Reliant does this under Shufflecake. What does it mean? The base operating system is in a read-only partition. If you want to update it, you have to flash it from a special virtual machine. And then, according to the password that you set at boot, you will see available more cubes virtual machines. And this gives you complete isolation and perfect usability for everyday tasks. Okay, this kind of concludes the overview. Future directions very quickly. 2025 was great. We pushed a lot of these changes and great. Growing community of contributors, performance boost, full crash consistency, garbage collection of unused slices. This was a nasty problem because previous generations of Shufflecake, if you allocate data and then you delete the data, that chunks of remains allocated to the old volumes, and it was difficult to deallocate it. This is all very hacky yet, okay? So we don't have a nice installer that allows you. This is on purpose, actually, because as long as we don't have complete trust in the security of the system, we don't want that, the random kids on the internet can get and run it, okay? I mean, we want technical people to be able to run these things. But eventually, we're going to change this and make a nice installer or whatever. Yeah, I mean, there are some dream directions eventually. and some more concrete plans for immediate improvements that we are actively working on. One of my favorite one is the virtual quotas and the anti-safe word. This is also interesting. Go to read the paper if you're interested, because this is cool stuff. And we are funding actually a Swiss no-profit association for you know, managing the project and grants, donations, and governance. So if you're interested, come to talk to us. How to contribute? Well, we are not on GitHub, of course, we are on Codeberg. We are not on X, we are on Mastodon, but we have a website, we have an email, and of course we have XMPP, which is not WhatsApp. Thank you for your attention.
Okay, thank you very much, Tommaso, for the entertaining talk. I think we have one question over there.
Thank you. Hi, thanks a lot for working on this. So it maybe will not shock you that I have questions about the realism of this. Because you're modeling cryptography in the presence of violence, and you essentially gave two examples, right? Like, people with guns, and there the question is, they will kill you. And so, you know, that there was a contrast in your story, but but realistically, because we were also thinking about, like, can we do plausible deniability? And the answer is no, we can't, because they will kill you if they think there's another layer, but there isn't one. So that's one problem, where you now have this problem. I need to prove I have nothing to hide, but if I can prove I have nothing to hide, they can demand a proof that you have nothing to hide. That's the one thing. And then the second thing, I don't share your optimism about the law. So under British law, if an agent of the state on reasonable grounds believes you're holding key, you're facing 2 years to 5 years in prison. I'm not sure 2/3 is not sufficient for reasonable grounds. I'm not a lawyer. I'm just saying, I would be careful with your confidence in various legal systems where this might be deployed.
Sure. Your first observation first. I listened very careful to the talk today, and I liked a lot. But we are looking at two different threat models here. In the model of you know, the Kenyan protests, whatever, that's targeted kidnapping. They know that you have something there, and if they don't find it, that's reason to be nasty. This is more against blanket seizures. You go to the US, you have to open the laptop at the border control, right? In those cases, I give you an example. We had some conversation with some officer from the International Red Cross, and they were interested in Shufflecake because, look, this is exactly why we use VeraCrypt right now, because we have a lot of operators in the Middle East, and they cross the borders with laptops full of sensitive data. In theory, we are the International Red Cross. We are protected from border seizures because of the UN threat is blah, blah, blah. But go to explain it to the angry Afghan guard, right? So what you want is something that you give something to the adversary, and the adversary doesn't care in digging too much further. This is for your first question. But I would say that there is something more, actually, because we don't have to forget that there are use cases that you don't really think of. And one that I would like everyone to think of is the following. If you are an investigative journalist in Guatemala and you are investigating against the cartel kidnaps you. They want to know your informants. You're gonna die regardless. But what you can do is to have some way to try to resist to the interrogation and say, this is all I have. And maybe you just give up half of your informants and you save the life of the others. This is about your first question. Does this satisfy your first one, or should I?
We can probably take this offline. Let me just do this meta point. I think it's really good to kind of think about cryptography in the presence of violence, but I urge everyone in this room to be very careful about what is your precise threat model and where you take this from.
Absolutely.
Your cases may be correct. I'm not just speaking from Kenya. We have other field sites in our project. All I'm saying is you need to be very narrow and very clear in that you're very narrow in what you are kind of protecting against, because it can cost lives.
No, sure. That's exactly, why we want to be careful with these things, right? And I mean, if I look at the model of the Kenyan protest app, I think it's two orthogonal models that they could even work together in theory. So we might even think of a system where you replace this plausible deniability of Shufflecake with another system where you have some alert instead of denying. I mean, it's two different models that can work according to your use case.
All right. I think we are out of time. If you have other questions, you can find Tommaso during the break.